you guys were testing, we have to check the same conditions. So we're switching from proportions to means. All right, we were doing proportions, which was z-tests. All right, so now we're going to means, which is t-tests, which is why I put the table B on your desk, because we're going to look at that. No, you don't really need it. I just want you to be able to interpret it if they do ask you a question, because we're going to use calculators probably most of the time. I would. Hold on to it. So you have to check for it's random. We have to check 10%, right? Unless there's an infinite number of something, then you don't have to check 10%. And then normal large counts. This time we don't do the NP greater than 10. What do we do for large counts for means? Greater than 30. If it's not greater than 30, what do we have to look at? The graph. Okay. So here's the formula for the test statistic that you're going to need. So this time it's our t-score instead of our z-score, right? And when we did it before, it was p hat minus p naught. Now it's going to be x bar, because we're talking about means, minus mu naught. So again, we get this value from our null hypothesis, divided by the standard deviation. And the formula for standard deviation is xx divided by the square root of n. So again, use S on your calculator. When you guys have to do one variable statistics, be sure you're looking at the S value for standard deviation. All right? And n is however many you have. We also have to look at degrees of freedom. So don't forget, degrees of freedom is n minus 1. And that's how you plug into your calculator when we do these. Okay. All right, so we've got a new battery company. Back to our batteries. And we want to test the null hypothesis. Mu is 30, so 30 hours is what we expect, versus the alternate hypothesis, where mu is greater than 30, based on a simple random sample of 15 new AAA batteries with mean lifetime of x bar. So we did our sample of 15 batteries, and that sample gave us 33.9 hours, and a standard deviation of 9.8. So the new test statistic is, so all we're calculating on this one is the test statistic. That's all it wants. So if all they want is the test statistic, it's just t, right? So x bar goes first. What do I plug in? 33.9. Okay, minus our mean. What do I plug in? 30. CC, don't zone out on me. And over the standard deviation of, what's Sx? Divided by the square root of n. What's n? Good, our 15 batteries. So this gives me a t-score of 1.54. Okay, 1.54. T-graph looks similar to the normal curve, right? It just has more area in the tails, is what we talked about. But when you sketch it, you can sketch it similar. So 1, 2, here's about 1.54 shaded over. So we want a p-value of anything to the right of that value because it's positive. So we're trying to find the probability. So this is the test statistic, right? But if I want now the p-value, we're going to find where t is greater than or equal to 1.54. So I want you to look on your chart just so you know how to do it on your chart. In case they ask a question on the AP exam, I want you to be able to read it. So start with your degrees of freedom. So degrees of freedom on this one, we had 15. So what's our degrees of freedom now? 14. We have a sample size of 15. Degrees of freedom is 14. So you go across the chart, and you're looking for 1.54. That's that area that we just shaded to the right of it. So look for 1.54 along 14, and it's in between two numbers, right? Yeah, 1.345 and 1.761, right? So look up at the top for your tail probabilities. So up at the top is between 10% and 5%. So that means that this our number is between, and we're never going to get an exact answer on the chart, so that's why I don't really like it. I mean, that's just me. But, I mean, maybe it's okay, because stats is all kind of rounding anyways. But, so it's between 5% and 10% for that area under the curve. So because, like, let's say that our significance level was 0.05, and we had between these two, would we reject the null? No, because it's somewhere in between. It could be bigger than that, so we would fail to reject the null. All right, so an even better way, of course, would be our calculators. So go to your calculator so you know where to find this. Go to menu, go to stats, go to distributions. So before we did normal CDF to find the area under the curve. Now we're going to do TCDF. So normal stands for Z, but TCDF. So our lower bound on this one is 1.54. Our upper bound is 1,000. We want that right tail. And our degrees of freedom is 14. Press enter, and we get 0.073. So that is in between the 5% and the 10% that we just got from table B. I find this a little more, I just like more accuracy, I guess. So 0.073 is what we get with the calculator. Don't forget to label it all when you plug it in, okay? When using table B, if you are using table B, and they give you a really large degrees of freedom. So as it gets larger and larger, right, they don't give you exact numbers. They give you like 40, 50, 60, 80, right? So round down on your degrees of freedom when you're finding that p-value, okay? If you're using table B, round down on your degrees of freedom. And of course, then use your calculator, even better. Yep. Okay, so let's go through one whole test, and then we'll be good to go. And you guys have one problem to do in class. No. What? You do have homework, yeah. All right, here we go. Let's go through this one time. So the level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along the stream. Here are the results in milligrams per liter, or mg/L. And we want to find a dissolved oxygen level below 5 milligrams per liter, or if we do, then that puts aquatic life at risk. All right? So, do we have convincing evidence at the 5% significance level that aquatic life in this stream is at risk? Okay. So, we need a null hypothesis and an alternate hypothesis, and we have to state what our mu is this time. So, just so you know, we want to test a claim for our state about the true mean dissolved oxygen level mu in the stream at a 5% significance level. So don't forget in your state to talk about what mu is and your significance level. And then we need a null hypothesis and an alternate hypothesis. So Tyler, what's your guess for the null hypothesis? What do you think it is? Jet, what do you think it is? Okay, good. 5 is good. Mu, though, because now we're doing means, so mu is equal to 5. Alternate is the interesting one. Jet, what do you think for the alternate hypothesis? Okay, good. It says right there, oxygen level below 5 puts aquatic life at risk. So that's what I want to know. Do I have less than 5 milligrams per liter. All right, if conditions are met, we should do so last time we did a one sample z-test for proportions. So Taylor, what do you think this one's called? Yep, 4. Very good. So it's a one sample t-test for mu. Okay, so we check random, and we go up to the top, and it says that he's doing randomly chosen locations along the stream. So we have a random. 10%. So this one's kind of interesting. How many locations could we check on the stream if we like stuck in a little thermometer thing? Infinite, right? There's an infinite number of locations. So anytime you have an infinite number, you don't have to check 10%. All right, so since it's infinite, no need to check. All right. And then we have large counts. So our n value, Owen, how many did we check? How many spots did we check? 15. So do we have greater than 30? No. So n is equal to 15, which is not greater than 30, so we have to check the graph. You have to draw a picture of it. So, yeah, you got to check it, unfortunately. All right, you guys, so you plug the numbers in, right? You go to plus a page, maybe. Add data and statistics and dissolved oxygen level. I'm going to check all of these. So here's a box plot. Pretty symmetric. I'd say that one's actually pretty normal. Histogram. And probably the best one that I think is easiest to read, because that's pretty linear. Normal graph. So not skewed. So you guys, if there's no strong outliers or strong skewness, it has to have strong skewness. Actually, any outliers make it not normal. All right, so do draw a graph. You have to sketch a graph for that part. And then we would say that it's basically normal, so we're going to assume normality. All right, so we're going to do our test statistic. Because they gave us data, we do need to go one variable statistics in order to get the information. So if I go back to my table, go to statistics, stat calculations, one variable stats, and put in your list. So here's our x bar, right, that we're going to use, and our sx. So make sure you don't use this one, but you do use the s one, so we can plug in our numbers. Where did I put my sheet? Right here. All right, so from one variable statistics, we have 4.771 minus 5. We got the 5 from the null hypothesis. Divided by the standard deviation, 0.9396, divided by the square root of 15. Plug that in, you get negative 0.94. Okay, then you can either use the chart or you can do TCDF. So this time it's negative, so if you picture the graph, we're drawing to the left of that number, so our lower bound is negative 1,000. Our upper is negative 0.94. And this time when we substitute in, guys, it's not mean and standard deviation. What's the last thing we plug into our calculator? Degrees of freedom, which is 14 on this one. And we get 0.182. Is that a small enough p-value to reject the null? No. All right. So our conclusion is because the p-value 0.182 is greater than alpha, we fail to reject the null. Always say it like this, right? We either reject the null or we fail to reject the null. We do not have convincing evidence that the mean DO level in the stream is less than 5 milligrams per liter. Both sentences are important, you guys. I also want this sentence about we either have convincing evidence or we don't have convincing evidence, okay? For part B, so given your conclusion to part A, which kind of mistake, a type 1 error or a type 2 error, could we have made? Explain what this mistake would mean in context. So if we fail to reject the null, is that a type 1 or type 2 error? Could be a type 2 error, right? Fail to reject the null could be a type 2 error if we messed up in our data, right? So because we failed to reject the null, we could have made a type 2 error. If we did make that type 2 error, that means that the true mean is actually less than 5 milligrams per liter, right? We just got evidence that told us otherwise. That's why we did not do that. Make sense? Just a review on the type 2 errors. And my little guy is gone. Come back. Come back. Oh. Minitab, you guys. So if it looks a little different, you got to be able to read this. So mu equals 0.5, that's your null hypothesis, versus less than 0.5, that's your alternative hypothesis. We've got our n, our mean, our standard deviation that you would want to use. They give you a t-score and a p-value already. So make sure you can just read those and plug them in if they give it to you that way. Of course, your calculator does the whole t-test for you. You can choose either data or statistics to enter, but you have to know your actual statistics. So if you guys want to find that on your calculator really quick, you go to stats, stat tests, and t-tests. Okay? And then you can choose data or statistics. So data means you have to have a list already plugged in, right? Statistics, so if you guys go to statistics, that's where you would plug in the null hypothesis. Yeah, go to stats, press OK. So you plug your null in, you plug your x bar, so whatever you got for that, your sx in, your n, and then you have to say if it's greater than, less than, or two-tailed. By the way, if we had done a two-tailed test, what would we need to do here? Double it. So pay attention if it's two-tailed, and don't forget to double your p-value, because it's both tails on the graph. Okay, your homework, you guys, this part is multiple choice. I'm giving you one test that's one-sided, another test that's two-sided, and then a confidence interval that goes with 77 to make sure you understand that part. All right? And I have one in class for you today.